All right, so we're going to switch back now a little bit to some more hardware stuff, and one of our vendors, and a little disclosures. Scott's here, and he's going to talk about heated sample lines, and he's with O'Brien, which is part of the universal thing that Bob talked about earlier, and they're owned by Amatec, and you can get all the hierarchy of when all this happened. But O'Brien's been around for a long time. You can talk about that. But they're one of our heated sample line vendors. And so Scott Ruben's here to talk about that. You just clip that on. Stay in the box.
My name is Scott Ruben. I'm with O'Brien Corporation, which is part of Amatec. Amatec has about 110 companies right now. They divide us up into 2 divisions, and then within those divisions, they create these business units, and they group companies that have similar, that serve similar fields. And so our business unit with Bob, I don't know where he is, has Universal Analyzer, which also have one or a company in North Carolina. And so we've got 5 companies. We have another sister company that's part of that's attached to our building called Cardinal UHP. They do ultra high purity cleaning of tubing for the semiconductor and biopharmaceutical field. So these are the topics I'm going to go over. So O'Brien's been around for a little over 50 years. We, besides heated tubing bundle, we also make heated enclosures. We make convection heaters. We make instrument stands, soft enclosures, a lot of other things. But this is just going to focus on tubing bundles or umbilicals. These are the topics that I'm going to hit. So over 50 years, this shows some of the other product lines, our instrument enclosures. This is our main facility in St. Louis, Missouri. So we've got tubing bundle and then the enclosures and the instrument stands, like I said. If anywhere along the way, if I'm going too fast and have questions, just stop me like you have everybody else. So what's the purpose? Everybody knows it's to bring that sample from the probe, bring it down the stack, and deliver it to the analyzer equipment and keep it at a specific temperature, above a certain temperature. So the 3 main styles of probes, everybody knows, it's already kind of been gone over. So for us to properly design a heated tubing bundle, these are some of the things that we need from the customer. So ambient temperatures, maintained temperatures, maximum inlet temperatures. These are all the things we need to be able to figure out what tuber tubes, what electric tracing we need to use, circuit lengths, breaker sizes, if you have a hotter than normal inlet coming in. So these are some of the things that we need to do. We also have, I'll go over later, we have different end preparation options, jacket materials and colors, and we do offer special printing on the outside of the bundle. Did I skip one? For tubing, the 2 main types of tubes are PFA Teflon and the 316 series stainless steels. We do offer other alloys, so 625, 825, 400, those other ones. We also offer different ID surface preparations. So as I said, Cardinal UHP is one of our sister companies, and through them we can offer chemical passivation, which would pass any CFOS or O2 cleaning methods. We also do passivation with silicone inert. I think Bob had talked about that earlier. It's another company that we work with that does a vapor deposition on the inside of the tube. So we will first passivate it to make sure that surface is very clean, and then have this vapor deposition done. Cardinal also does electropolishing. Does everybody know what electropolishing is? EP? Yes, no, maybe. So EPing is kind of the opposite of plating. So we're actually taking material off the surface of the tube. And so what we're doing is we're taking that, we call it the free iron. So the iron near the surface, we're taking that off the surface. And it's a chemical and electric operation where we're attracting that iron and removing it from the surface. And so what that does, it does two things for you. The iron is what is going to corrode, so you're taking that corrosion layer off. And it also tends to smooth the surface out. So in general, we're able to cut the RA, or that surface roughness, in half when we EP. So if it starts off at 40 RA, we can cut it to a 20 RA. And all that helps with getting a better laminar flow. It helps with the absorption, desorption times. And then last, we can do a combination. We can EP it, and then we can have it sent out for silicone inert treatment. Any questions on that? So a couple recommendations when you're giving us information on what we need to use, or what parameters we need to use to design your tubing bundle. The biggest thing that we see is that whatever maintain temperature you need, don't overinflate it. Because if your dew point is 180 and you're telling us you want to maintain 300, well, we can do it. In general, the higher it maintains, you get shorter circuit lengths, you draw more power, you need larger circuit breakers. We're having to use more expensive tracers in general. The higher the temperature of the tracer, the more expensive it is in general. And also, it tends to lead to a shorter tracer life. All electric tracer has a finite life. In general, the higher the temperature, the higher the current draw, the higher the temperature exposures, the shorter the life. So a tracer used for just freeze protection is generally going to have a longer life than one used for 250F maintain. And then Teflon tubing. So as everybody knows, Teflon is porous. So we want to reduce any possibility of permeation, of getting CO migration through the tube wall. So the two big things are use the heaviest wall. So the heaviest wall PFA we use is an 062 wall. We also offer 030, 040, 047, and then 062. Go to the heaviest wall, the thicker wall resists permeation more, and then use the lowest maintain temperature. As that Teflon gets hotter, it becomes more porous and more of a path for CO to migrate through. So tracer selection. So we will select a tracer based on the maintain temperature, circuit lengths, voltage, all those things. And these are the four main styles of tracers we use. So self-regulating, power limiting, constant power density, also called constant wattage or CPD, and series resistance. So I'll go through each one of these and kind of the pros and cons of each one. So self-reg, the pros are can maintain up to 250F. There's actually a new tracer we can do up to 400F now. But does everybody know how self-regulating tracer works, or at least the basics of it? Because it's kind of a misnomer. A lot of people think I get a self-regulating tracer in a tubing bundle and I need it to maintain 250F. Look it up. and it's going to maintain 250F all year long. And it doesn't, what it does, it changes its power output with temperature. So most self-regulating tracers, or most self-regulating tracer companies, they rate their tracers at 50 degrees F or 10 degrees C. So a 20 watt per foot self-reg, it's putting out 20 watts per foot at 50 degrees F or 10 degrees C. 10 watt per foot, same thing. And as it heats up, it puts out less power. And depending on which tracer you're using, that temperature curve changes. So as you go to higher and higher temperature tracers, that gets flatter and flatter, that output curve. So the negatives on self-reg tracers are that there's an inrush. So an inrush is when you first turn it on, it's that inrush, or that increase in current for a very short duration when it turns on. And the colder it is, the more it's going to draw. And that's only when you first turn it on. Once it's cycling, the inrush doesn't happen. So if you have a 100-foot umbilical, 20 watt per foot, and you turn it on in the middle of the summer, it will draw far less of that inrush than if you turned it on and you're in Edmonton and it's minus 40F. It will draw far more. So the reason that's important is that affects your circuit breaker sizing for cold startups. And if you have multiple lines, multiple umbilicals, you maybe want to stagger them on your initial cold startup. So how self-regulating works, and I'll just kind of go over the basics. So you have essentially two bus wires, and in between that bus wire is a polymer, and that polymer does not conduct electricity. But when they're making the tracer, that polymer, they'll mix in carbon black, which does conduct electricity. And so they mix that carbon black up in that polymer, then they extrude it over these two bus wires. So you electrify, put electricity across the two bus wires, and the electricity is looking for a path of least resistance. So what it does, it sees a piece of carbon black, and it essentially jumps or arcs to it, and then to the next one, until it reaches the other bus wire. So it's an electric chain that it produces. And as it's making those jumps, there's resistance. That resistance produces heat. So you get a bunch of these electrical chains happening all down the length of the tracer. So that produces heat, tracer starts heating up. As it heats up, that polymer expands slightly. So it pushes the bus wires apart, which then pushes those bits of carbon black, so there's a bigger spacing. Now you can't make as many these electrical chains. So it cools down, contracts more, and just does this over and over and over, all down the length of the tracer. So back what I was saying, self-regulating tracer, what that temperature window, where it's going to operate in, depends on your ambient temperatures, how many tuber tubes and what sizes they are, voltage, a lot of factors. The greater your ambient temperatures, coldest day of the year to hottest day of the year, the bigger that window of operation is going to be. So if we were designing a bundle to maintain 150F, we're going to shoot for 150F on that coldest day of the year. And on the hottest day of the year, anything above that, it's going to be above that. And so maybe it'll operate between 150F and 200F. If that's acceptable to a customer, they don't have to use temperature control. If they want a tighter temperature band, they can use a temperature control. If you're using a tracer at its maximum temperature is 250F, and you want to maintain 200F, so you're hitting 200F on the cold day. On the hot day of the year, maybe you're hitting 285 or something above it's acceptable, then you have to use temperature control. So just because it's self-regulating doesn't mean you don't need temperature control. So our lowest temperature tracer, which is a straight freeze protect tracer, is a Raychem BTV tracer. And then on the right side here, on all self-reg tracers, this is that output curve. And so on this tracer, they've got a 3 watt, 5 watt, 8, and 10. And so if we pick the 3 watt, which is a little hard to see, but it's D. It's right here. There's along the left side here, here's the output in watts per foot. And then along the bottom, it's the temperature. So 50 degrees F, 3 watts per foot, that's where it is. And then as it heats up, it's putting out less and less power. So when we go to the next hotter tracer, you'll see the temperature curves are a lot flatter. And as you get to hotter and hotter traces, those curves are flatter and flatter. So that's the next one. XTV can maintain up to 250F. And like I said, there's one more I don't have on the slide, but it's an HTV, can maintain up to 400F. But at 400F, it's not putting out much power, so we're not generally able to use it for temperatures above about 150F, just not putting much power output. So the next style is called power limiting. So power limiting has self-regulating qualities, but it's a zone style tracer. Everybody know what a zone style tracer is? So it's different than a self-reg. So it has self-reg qualities, but zone style tracers, they look similar, but internally they are made up of individual parallel circuits. So they have these parallel circuits are called, they're set up in things called zones. So you have zone lengths between 13 inches and about 49 inches. And every zone essentially operates, it's its own circuit, but it's a parallel circuit. And you have the next one and the next one. Why that's important is when you're putting a tubing bundle in and you're using a zone style tracer, you have to be concerned at the very ends where you're cutting that tracer, only complete zones make heat. So if you're cutting the tracer from that point back, in between each zone is called a node. From that point till that next node, it's not producing heat. So you want to make sure when you're cutting your bundle, you have extra tracer coming out, so you know that the tubing bundle or that process is heated all the way to the end of the bundle and then outside of it. So it depends on which tracer. So this one, which is VPL, it's not a marking, but there's an indentation. So once you know what to look for with VPL, you can rub your fingers along it and you'll feel an indentation. That indentation is the node. You can visibly see it, but it's a little harder to detect. But once you know what to look for, yes. But you need to cut the tubing bundle back. You have to cut the outer jacket and insulation, get down to the tracer to find it. So this is a VPL tracer, can maintain up to 455F. But with VPL, it's not a straight 455F. It depends on the individual wattage and voltage. So this here shows, in general, the higher the watt density, the lower the maintain. So the 20 watt can only maintain 300F, where the 5 watt 120 volt can do up to 445F, and the 5 watt 240 volt can do up to 455F. So any questions on that anymore? So that's the only power limiting tracer we have. And this kind of shows that individual, those parallel circuits. So this shows, so this represents the tubing bundle. And then down the center here is the tracer. Those little notches are the nodes. So if you were to install the bundle like this, from this point to this point, there's no heat. So you don't want to do this. You want to install it like this, where you've got a complete zone exiting the bundle. So the next style is a constant power density or constant wattage density, also a zone style, but it always puts out the same wattage no matter what. So this is our T-Series tracer, which we have made for us. It's a 400F 204C product. To your question about the nodes on this you cannot detect. The only way to detect the nodes on this is with an electrical check. So you get to the end of the tracer. So you have 2 bus wires, you have dielectric in between, you have a heater element wire that runs around the outside. So you push the ground braid back out of the way, get to the 2 bus wires and the heater element wire, use a multimeter, and you measure the resistance from the heater element wire to one of the bus wires, record that value. to the other bus wire, record that value. In the lower of the two, we've got a chart. I don't know if I have it in here. Here it is. You would then, whatever that number is, let's say that's 200 ohm, the lower of the two. Let's say you were using this TY18 tracer. You would then divide that by 50.074 because it's the resistance of that is 50.074 per inch. That will tell you how many inches away you are from that next node. We've tried having it marked, and since this tracer has a external braid, that braid moves around and it's too difficult to try to accurately get that. So then the next style is series resistance, which is we use an MI. Everybody know what an MI tracer is used in the field a lot. Looks like a metal tube. It has either one or two heater elements in it. Really, really high maintain and exposure temperature. The real downside about MI tracer is you buy it as a specific length. It already has end terminations and power connections built onto it. If you cut it, it's a very difficult repair to make. So you buy it at a specific length, and it's really made for field install. It doesn't lend itself so well to tubing bundle. Temperature sensors, so we use thermocouples and RTDs, whichever the customer wants, generally either a J or a K thermocouple, and a 3-wire RTD 100 ohm platinum. So tubing bundles. So we can do, especially with CEMS umbilicals, since CEMS umbilicals tend to have a lot of extra things in them. The customer also wants extra blowdown tubes and things to operate solenoid valves and different wires and cables. They tend to be larger bundles. So this has the what's required to for the process tubes and maybe some spares in here. And then on the outside here is what the customer has told us. Can you throw in these extra wires and cables? So they tend to be large. About 10, probably 12, 14 years ago, we started saying, okay, we can also offer this in a 2-bundle approach, meaning one bundle will have your heated tubes, your process tubes. The other bundle will take all of the unheated materials, tubes and wires and cables, put that in a separate tubing bundle. And there's pros and cons to each. I think my next slide says it, but so the pros about the all-in-one are you're installing one bundle, you're buying one bundle, and the cost is less, the upfront cost is less than a 2-bundle approach. Where the 2-bundle approach has its advantages is long-term, 10 years, 20 years, 30 years. Like I said earlier, all heat trace has a finite life. Maybe it's 5 years, 10 years, 15 years, but at some point that heat trace will fail. If you have an all-in-one, now you're replacing this large tubing bundle with a lot of extra things that are still good. Tubes and wires and cables are all still good. It's just the heat trace doesn't work anymore. So that's when the advantage of this comes into play, because then this stays in place and you're just replacing the tubing bundle with the heated portion. So like I said, more upfront cost with this, but over the life of a stack of 40 years, 50 years, where you may be replacing that heat trace 2 times, maybe 3 times, depending on what your maintain is, then this is definitely a less expensive option. Any questions on the 1 or 2 bundle approach? Yeah.
15 years and I've lost 2 out of 4. Wondering if I should be prepared that the other 2 either near life or are they going to go another 6?
Not so much, because it depends on a lot of things. But I mean, it depends on, so if you have a 400F umbilical that's 100 foot versus a 400F umbilical that's 250 foot, the higher current draw on the longer one definitely will generally lead to a shorter life of the tracer. So you're thinking about the wattage, the higher the maintain, the higher the current draw, and then other factors like higher inlet temperatures. If the bundle has when it was installed, you want to make sure you're using rigid support that doesn't allow the bundle to move, because slight movements of the electric tracer will lead to failure over time. And the more movement, the shorter the life will be. And my analogy I like to use is a paper clip. As you bend it back and forth and back and forth, it fatigues and it breaks. Even though electric heat trace is stranded wire, it over its life of it moving back and forth, it will fail. So we have a lot of customers that figure on a 400F bundle 5 to 7 years, and then after 5 to 7 years, then they either replace it or maybe they buy one and they put it into storage for a spare. Because as long as, and I'll go over this a little bit later, as long as I don't run out of time, tubing bundle, as long as you keep it away from getting external damage, vehicular traffic, and you keep it inside, away from moisture and all that, it doesn't degrade. So having, we've had customers that have tubing bundle that they'll put on the shelf for 5 years and then put it into service because they just have it as a spare. So 5 to 7 years for real high temperature, high current applications. We've had freeze protect customers that are just 50F maintains that I'll get a call after 25 years and they'll have questions about it and it's still working. But it's hard to say. I would say 400F, 5 to 7 years, maybe up to 10 years. It just depends.
15 years we've got out.
That is really good. Yeah. Yep. Absolutely. So like I said, and I've got some slides on that, but yeah, so installation has a huge factor on the life of the bundle. And I'll go over a little bit of that later, but yeah, when tie wraps are okay, but we prefer, and I'll go over that, 1/2 inch wide, outdoor rated, and I like acetal as a material. There's a brand that I like that I've got on a slide that they're made for the overhead power line industry, and they've got a 20-year plus life. But whatever kind of clamp they're using, you don't want to compress that thermal insulation. When you start compressing it, then you're defeating the purpose of that insulation, which is to reduce that heat loss, and then not using cable ties or anything that has sharp edges which can cut into the jacket. Here, I already went over that. So most of our customers, we make the tubing bundle, we call it flush cut. We make it, we saw cut the ends. It's in the field, they install it, they trim back the ends, they do all the prep and weather sealing. We do offer a lot of different end prep options where we can seal, factory seal and expose to a certain amount, whatever the customer wants. So it makes it a little more turnkey. We have it where we can do both ends. And what I tell customers on, if they want both ends we call it factory sealed, is I only recommend doing that if it's a shorter line or you're replacing a line that you've taken down and you've been able to do an exact measurement. Because if you order a 250-foot line, we've prepped both ends, you install it, and it's really only 230 foot, you're going to be cutting off some of that work that you've paid for that we've done. So I recommend, if you want to get an end finished, have just the shelter, the power end done, and then cut any excess off of the other end. I'm also showing you here, we can do, all tracer has a maximum circuit length depending on the watt density and the supply voltage. When you get to that length, you can't go any further. And so what we can do is we can essentially double the tracer. And in the factory, we'll put end terminations inside the bundle so we can double that circuit length. It's 2 independent circuits, but it's 1 complete tubing bundle. You have to bring power to both ends. We can put a cable in there, bring power to the other end. If it needs temperature control, you have to temperature control them separately, but at least you would have a single tubing bundle 500 feet long that you're not having to splice in the field 2 bundles. These are all the colors we offer. We've got 13 colors plus black. So So a lot of customers either like to have a company color, or depending on what they're measuring, have that outer jacket a different color, so you can just look and say, oh, that's measuring NOx, or that's measuring mercury, or whatever it's measuring. So that's an option. And we've got two different types of jacket. We've got PVC and urethane. This is the urethane colors. PVC, we've got 5 colors. We generally push people to urethane with colors because we have a lot more. It's a lot more readable. We don't keep the PVC colors in stock. So once we've designed it, we've made it, we shipped it to site. Once you get it, there's some things that we recommend doing when you get it. First one is this what you ordered? On the side of the wood spool, there'll be a plastic placard that'll say the model number, the quantity, all the stuff. So make sure what you ordered, you got. And the second thing is there any visible damage? Shipping damage is more common than I would like it to be. And shipping damage usually is pretty easy to pick out. Either the wood spools, one or both are broke, part of the flange is broke, or there'll be forklift damage that's usually pretty apparent. One of the forks went into it and there's a big cut in the jacket. Sometimes we can correct it on site, running a piece of heat shrink down, sealing it up. We want to make sure that you look at this stuff right when you get it, because usually you're ordering it in advance. And if we need to remake one or something, we want that extra time and not day of installation. Whoa, this looks like it's damaged. So giving you and us that time to correct it. Also, if there's a cut in the jacket and you're not installing it for a couple of weeks and it sits out in the field, water gets in there. I've got this on a bunch of slides. The #1 reason for pre-insulated tubing bundle failure is moisture getting in. Moisture gets into the thermal insulation, which then reduces that insulating quality. You get more heat loss. So at a minimum, you're not going to be able to maintain temperature in that area. It could be as much as to make the tracer overheat in that area, maybe make it fail, maybe overheat tubes. So any cuts we want to address right then. Slide. It's also good to do a tracer check. So get to the ends of the bundle. If the ends are flush cut, we'll put shipping caps. There's vinyl caps over the ends. Pull those off. Do a quick check of the tracer. Just do a resistance check and a Megger test. Record those values. Put the shipping caps back on. Tape them in place. If it's going to be stored, we recommend storing it inside and away from traffic. If it has to be stored outside, get it up off the ground, put it on a wood pallet. We don't want it sitting directly on the ground. The main reason is when it rains, especially if that wood pallet is flat, it sits in a puddle, the wood starts to break down, you start rolling it to use it, the spool falls apart, and then you've got a big mess. It's really difficult to re-spool them. So went over that. Store indoors, keep and sealed, keep away from traffic so no one runs into it. So day of install. So these are some of the things we need to do. The biggest ones are, yeah. So we offer, and offer being me, installation support. So I can come to site and spend a half a day and meet with who are the install crew and go over all the points and correct ways, the do's and don'ts on installing. But we ourselves don't have installation crew. We've got companies we work with that do installations. So we can recommend. Yep, absolutely. Yep. So these are some of the things that we need to do. The biggest one is that your crew, whoever's going to be doing the install, everybody understands what's going to be done. So having enough people and people educated on what's going to be done. Kellum grips will go over. Everybody know what Kellum grips are. They used to call them, it's those wire mesh things. They used to call them Chinese finger grips for those large mesh things. And we require that on any vertical installs more than 50 foot. So when you're pulling it into place, we want to use those Kellum grips and attach the cable or rope to the Kellum grips to pull it into place, not tying a rope around the bundle and compressing that thermal insulation. So don't twist the bundle, use wide bands or clamps to hold it in the final position. The supports on horizontal runs, no greater distance than 6 foot, and on vertical, no greater distance than 15. So we want those supports at that distance or closer, mainly to keep it from moving around due to the wind. Supports need to be rigidly held. We've had some customers in the past who will attach them to guy wires, and they will fail attached to that. Even though that guy wire may be pulled really tight and high tensioned, that it's hanging below it, it will allow it to move. And one installation that comes to mind was the installation started inside of a building, and they had rigid support going vertical through the building. When it reached the roof, it went up and went diagonal over to some stacks. And it was about 75 foot diagonal. There was a guy wire, and it hung below, and then it hit the stack and it went up another 20 or 30 feet. And after a couple months, they all started failing. I think there were 8 of them, and went to site, and you could see when the wind would blow that where it came up through the roof of the building and it went diagonal, you could see that movement. And I told them that's where it failed. And they said, no, it can withstand that. So after they cut into it, the tracer actually had severed. But if you think about it, it was being held rigid like this, and this part was allowed to move. And it took 2 or 3 months, and then it failed. Have you guys seen that? Or I don't know if you guys have seen that. Okay. And then so fully support all bends. Bend radius 8 to 12 inches. In general, 2-inch bundle or smaller. 8-inch bend radius. Anything above that 12-inch bend radius. Air gap. We need a 1/2-inch air gap between umbilicals being run, just to get good air circulation. Once it's installed and clamped, do a good visual inspection. It's not uncommon during installation, the jacket gets cut, goes around a bend, hits a piece of unistrut or something. As long as it hasn't rained and you address it quickly, it can be repaired and it doesn't hurt the bundle at all. So this shows normally what goes on is you got the spool, you put a pipe through the middle of it, you lift it up off the ground so it can freewheel. You get it near the stack where you're going to be installing it. Use these Kellum grips. You have some kind of pulley system, and you pull it up the stack. We have a few customers that put it to the top of the stack and go down. It's not sure why they do it, but these are those Kellum grips. These are the cable ties that I like. It's called black acetal, but they're 1/2-inch wide. I can send a link to the company that makes them. Another style clamp I like are these for if you're going to be connecting to unistrut. It's a pipe clamp, but it's got a plastic insert, and it's got a single pinch point, so it fits into the unistrut, and they're sized about every 1/4 inch. And so you'd put that around the bundle and then fit it into the unistrut. This shows just going through a ladder tray. So this shows one of the installs that I went on. So they're putting their first Kellum grip on. They've got the bundle here with a pipe through it, lifted up off the ground. They've got a rope going up to the top off of a pulley. These are kind of dark, but they're starting to pull it up the stack here. And at least no more than every 50 feet, they're stopping, putting another Kellum grip on, attaching it to that rope, and then pulling it up the stack. Once they pulled it up the stack, then we get the rest of it off the spool, kind of lay it out on the ground. And what I like to do is then on that end, feed that into the shelter, get it lined up, get it close to the equipment where they need to be, maybe trim the end back. If it's got a factory finished in, then they can bring it all the way up to the equipment. And then starting at the shelter, I like going from the shelter back up to the top and adding your permanent supports going up and then cutting the excess off at the top. So this shows up at the top, going through the probe, and then they're working their way back up, putting the permanent supports. And I tell people that, so the Kelm grips are not a primary support. They can be used as a secondary support. So using those pipe clamps or cable ties, but leave the Kelm grips in place and tie them off. Have them as a secondary piece of support. You've already paid for it, leave it in place. And I've got the next slide will show that. So this shows going into the shelter, connecting to their equipment, bringing it as close as you can to the equipment, because you want that heated sample getting as close as you can to the analyzer equipment. This slide right here is what I was referring to. So this is looking at the top through the grating, looking down. And so you've got your pipe clamps here, here, and here. Here's your Kelm grips where they've just tied off. They tensioned it and tied it off and used it as a secondary piece of support. This is what we don't want to do. We don't want to just tie a rope around the bundle to cinch it, to pull it up the stack, because once you compress the insulation, it's not going to go back to its original size. And this is showing, so you don't want to do this. This is the Kelm grip, which you do want to do. This one is a properly sized pipe clamp where you're not pinching anything. It's a little hard to see, but this clamp is not large enough, and it's pinching the jacket a little bit. And over time, with the just movement of the stack and vibrations at the plant, it could work its way and cut through the jacket. This one, there's no air gap in between. This one, again, it's undersized and it's kind of pinching the jacket. This one's properly sized. All my own time. Okay. So this is, I was thinking about, you want to support the bundle, especially at bends. So this was 15, 18 years ago. I was at a plant and they came up with this. And I thought it was a great thing. This is, they took a plastic PVC elbow. It's like a 3-inch or 4-inch or 6-inch elbow, cut it down the middle, and then cable tied it to the inside. Gives it really good support, because what can happen on bends, even though they've supported it here and there's a support right here, over time, that bundle could slide down the stack. Then you're going to get a harder and harder bend at this point, and it could be enough where you're pinching the tubes, if they're Teflon tubes, or damaging the tracer. So this is a super inexpensive, simple way to support a bend. These are not great pictures, but this is showing a tubing bundle, and then they've stopped it short. This is an analyzer cabinet. They've got the last 6 inches bare tube. Bring it all the way into the shelter, all the way into the cabinet. Processed fluids, but especially gases, lose heat quickly. So don't pay for all this money on a tubing bundle and that end up having that last section not heated. The same reason with the zones. You want to make sure you have a complete zone exiting the bundle. This, they've just grouped, it was like 6 or 8 bundles together, heated bundles together, put one big tie wrap around it, and you've got the chance of them overheating in the middle. This one, I'm not sure why they did what they did, but when they made their bends, they cut through the jacket, through the insulation down to the process tube and tracer, bent it, and then went back. And I think they were doing it to get these really tight bends, but then they left it like this. They didn't go back and hand wrap insulation in any jacket protection, any weather sealing. And I got a call after, I don't know, a couple months of use, and they said these aren't working anymore, and went out there, and it's pretty obvious what was going on. This one, the last one here, is a great example of that MI tracer I don't think is a great fit for tubing bundle. Like, as I said, MI tracer, you cannot cut it to length. You buy a specific length, you buy 150 footer, we put it in a tubing bundle, you get 150 footer, you got to make do. So they had extra bundle, they ordered too much. And so this is their shelter. Came down from the stack, they ran down here and back up. And the biggest problem with this is that you've got this low point right here. If they would have just wrapped it around the shelter in like a slow descending order and then went into the shelter, it would have been fine. But This ran, I think, for about a year, and then it plugged. And so they sent me a picture, and it's pretty obvious what was going on. So if you have a bundle that you can't cut back, if you can reroute it to take extra distance, or if you have to spirally wrap it around something, don't have have the low point at your equipment, not in the middle of the line. This one shows bringing a tubing bundle all the way into a enclosure. This showing nice air gaps in between the bundle. This showing sealing the end of the bundle. Again, a downward slope all the way into the enclosure. So troubleshooting. So I do most of the troubleshooting, and I've been doing it for 15 years. And so this is my highlight of all my troubleshooting that I've done over the years. So this was a line that was 2 tracers inside. It was too long for a single circuit. And so it was 2 tracers end to end. We'd put the midpoint terminations. We'd run extra wires to the end, connected to the tracer at the far end. So you had 2 heating circuits. I think this was about 650 feet long. And we'd finished both ends. So it was a true plug and play install. So they had installed it, and they had extra bundle at the probe end. And so they didn't contact us. They just cut like an extra, or the last 20 or 30 foot off, remade the connection to those lead wires coming from the shelter, which is fine, but they didn't do a very good job of making that connection. So the technician that was with the installer told the electricians on site, it's okay to power it up. Powered up the first circuit, was fine. The second circuit tripped the breaker. So I told him to try it again, and it was an immediate trip. So the technician on site told the electricians that the person thought their breaker was bad and wire around the breaker. Terrible idea. I don't know why the electricians agreed to it, but they did. And this is what happened. They had a short when they remade their connections up at the top, and it vaporized about a foot, the last foot of the tubing bundle. I mean, it vaporized it. You can't even see the bottom of the probe in this picture. Took out the probe. The probe was just looked like a fire. I mean, it was just all soot inside. And I got this picture from the technician. Hey, can this be repaired? Asked everything what happened, and I said, and this was one of these bundles that's got 30 wires and cables and 6 or 8 extra unheated tubes, really, really expensive line. And I said, I don't think so. And so they said, can we pay you to come out and see if you can repair it? So I did. And so first thing I did was document everything. It was there. But I cut back to where the damage or the visual damage ended. So around here, just cut the bundle off just with a saw. Got to the tracer, did a resistance and a megger test, and it was fine, surprisingly. And then I did continuity on all the messenger wires and cables, and they were all good. So then I'm like, okay, the rest of this tubing bundle is good, but now it's too short. Now we're 2 foot away from the probe, plus we need extra tracer and wires and cables inside the probe box. So the way they had routed it, I said, can we reroute the last 50 feet or so to get some extra bundle? Thankfully, they were able to. We got enough bundle to bring it up into the probe box, did all my connections, and it worked. But so the reason I show this is not to rub the person's nose in this, but if something doesn't feel right, doesn't look right, you're not sure about something, ask questions. Don't assume. You can always reach out to us if during an install something doesn't feel right, or the installers you guys are using, if you're questioning what they're doing, reach out to us. But the biggest thing with this, besides the possible loss of like a $60,000 line, was if someone had been standing near this, they could have absolutely been hurt, significantly hurt, or worse. So these are some of the notes I have when I'm doing troubleshooting, things that I do to check. And I always start with the most basic stuff. You know, did it ever work? if so, how long does it work? What things have changed? What supply voltage do you have? And go through that. Any questions on any of that? So after it's installed, these are some of the things I like to do. So you've done your resistance and megger test before install. So let's do that again. Let's also check if there's any temperature sensors, check those. Go back and check all the weather sealing. Like I said, during install, it's not uncommon to cut the jacket. During installation, some installs may take a full day. And let's say they've got it halfway installed, it's lunchtime, and you've got the bare end of the bundle there. Don't leave that exposed. Take a trash bag, plastic trash bag, and tie it over the end, just in case during lunchtime it rains. Don't take any chances. You've got this money invested in the umbilical plus the install, which could be as much as the umbilical or more. Don't waste that. Take these precautions. So check all these things. Then check if you have a temperature controller, confirm it's working correctly. Check your supply voltages and all that. Make sure you've got your proper support. Bend radiuses are not exceeded. Then power it up. Set all the parameters on your controller and watch it hit temperature, turn off, make sure it cycles at least through a couple cycles and monitor it. And then like back here, anything that you're checking, any checks you do, write all these things down. So, because one of the recommendations is once per year, checking the health of the tracer, and checking the health of the tracer is the resistance and megger. Then you've got something to compare it to. Permeation. So with Teflon, I said earlier, there can be permeation issues. This is some of the burn-in things that over the years that we've been doing this, feedback that we've gotten, and so we've compiled this mainly from our customers. But we generally recommend just doing a DI water flush, even though lots of customers use different solvents, which probably work better. We haven't done that testing, so we can't say it. Plus, there's always the danger of solvents, and the person didn't disconnect power from the tracer, and you get an arc or something. And so, while solvent flushes, I know work because most of our customers use that for flushing the lines. Our recommendation is DI water flush, and then doing a nitrogen gas purge until all the moisture's out. Yep. Yeah. So the reason we used to offer FEP, we still do, but FEP, PTFE, and then PFA. And we've been doing umbilicals specifically for the CEMS market for probably 18 years. And over all those years, there's a handful of people that used FEP. So we generally don't even keep FEP. PTFE we offered for a long time because it is a little higher temperature than PFA, but we've had issues with some of our PTF suppliers where if they don't, I think what it's called, the curing and sintering process when they're making the tube, if it's not done right, some of the process fluids during the process of making the tube can embed themselves in. And years ago, we had issues with some of our suppliers, so we just went away because how you make PTFE versus PFA tubing is different, and you don't get that with PFA. So I don't know comparison PTFE versus PFA, given the same wall thickness. If one permeates more than another one, I don't know, just because we haven't used PTFE in so many years. So with PFA, we tell people use the heaviest wall, which is, like I said, our 062 wall, and the lowest maintain. As it gets hotter and hotter, those pores open up more, and there's more opportunity for CO migration. When there is CO migration with our customers, generally a burn-in takes care of it. Maybe it's a couple days, maybe it's even up to a week, and then doing a flush. There are a few that it just kind of flat lines out. They continue to get a couple parts per ppm, but it flat lines, and they're able to work with that if they're able to show that it doesn't change from that point. That's kind of out of our hands. I don't know what they do, and I don't know what with EPA what there is as far as if you can show that it doesn't change. Yeah.
Questions are.
Yep. Right.
My group doesn't regulate.
Yep.
I think
Okay.
that whole hearing period, what you're talking
Right.
about.
Okay.
I don't know.
So in general, there should be a point the CO should stop migrating because it's coming from the thermal insulation. All the major tubing bundle manufacturers use the same two manufacturers, and there's a binder that's holding those fibers together, that fiberglass insulation, and it's that binder burning off at higher temperatures when you get near the 400F. And so once those binders are burned off, then the CO should stop. And it's just, okay. So yeah, it is. And the higher the temperatures, the more permeable it is. But as far as a comparison with PTFE, I don't know because we haven't used it in so many years. Sure. Still that same procedure. All right. So these are kind of our recommendations. Visual checks, doing weekly, and it doesn't have to be some intense hour-long visual check. Just if it's a stack, looking up the stack, making sure it's not sagging or falling off, because we've had on those pipe clamps that are in Unistrut, we have had some where customers reported that after installation it walked out of it, and they've got 2 or 3 of the clamps hanging out of the Unistrut. So when that started happening, our recommendation was they make just little angle pieces for strut, putting those on either side so it can't walk out of the Unistrut. So since we recommended that years ago, I haven't heard of that happening. But just doing a weekly visual check, and then checking the temperature controller, make sure there aren't any alarms. And then monthly, same visual checks, same temperature controller checks, and then routing of the umbilical. And then annually doing the megahertz and resistance checks. So any other questions or anything that I need to go back over or stay within my time? Yeah. All right, that's all I have. Thank you.